Okay. So, today we start with the first technical topic, and that is state space search. So, let me begin by first putting this whole thing into perspective. I will just write this stuff at this end. So, we are looking at one aspect of AI, which we will call as problem solving. As we said, there are many other aspects that we will not cover in this course, for example, learning or using experience or reasoning with knowledge. We will focus on problem solving, and by problem solving we mean that the agent is in a desired is in some situation and wants to be in some desired situation. Okay. So, given to desired situation, and the task of the agent is to make a series of decisions or a series of moves which will transform the given situation to the desired situation. So, the task is to find these decisions, and that is a task we will be addressing. Now, in general there are two approaches to this. One is the one that we are following in this course, which is search or first principles based approach, which means that you have some kind of a representation of the domain and you simulate what would happen in the domain as a consequence of your decisions, and then try to find those decisions which will achieve the goal that you are aiming at. The other is knowledge based, in which you are trying to exploit knowledge which has been accrued by some means essentially. So, in general, of course, knowledge is derived from experience, either your own experience or somebody else's experience, and conveyed through in the form of books and lectures and things like that, or stories. But given the knowledge, we want to exploit those techniques. The knowledge based techniques themselves could be classified into two kinds, which is memory based and rule based. Memory based techniques try to exploit stored experience directly essentially. So, this area is also known as case based reasoning, and in fact, we have a separate course which will be offered next semester called memory based reasoning in AI, which will focus entirely on this approach to problem solving. And what the memory based approach does is that it stores experiences. And what do we mean by experiences? Each case, as we call it, is a pair made up of a problem description and a solution that worked for the problem description. So, every time you solve a problem, it could be a human being solving a problem and putting the case into the memory and so on. So, every time you solve a problem, you store the problem and the description and the solution description into this case space, and when a new problem occurs, you retrieve the best matching problem description and use or reuse the solution that was stored along with that essentially. So, that is a general idea of using experience. That is how we learn many things, for example, how to make sambar or something like that, or how to solve some kind of integral equations, whatever the case may be. The rule based approach is, on the other hand, does not use experiences directly, but relies on rules, or you might say nuggets of knowledge extracted from experiences. And very often a rule based approach needs a human intermediary to convert experience into rules. So, the standard approach that was followed in expert systems, we talked about Dendrol and Mycin and Prospector. These were rule based systems, and the way that they were built were that so called knowledge engineers went and spoke to domain experts and tried to elicit from them the knowledge that they use for solving their problems. It could be diagnosis or whatever the problem was, and try to put that knowledge in the form of rules essentially. So, we have knowledge based methods as opposed to search based methods, and we will be largely exploring search based methods in this course essentially. Of course, it is not as if search based methods are devoid of knowledge, because we have to still model the domain, we still have to create the platform on which this search will happen. To that extent, we do need knowledge for search based methods essentially. As we move along in the course, we will see that search by itself is not a very efficient means of solving problems, because we will see that we run into something called combinatorial explosion, that number of possibilities that we have to explore will be too high essentially. So, very soon, in fact, in the next week itself, we will introduce some element of knowledge into search. We will try to see how search can be guided by some kind of domain knowledge, and we call this heuristic search, and the knowledge that we will use is called heuristic knowledge. After that, we will move towards standardizing the representation of the domain. So, when we begin with, we will just make some ad hoc assumptions as to how the domain is going to be represented, because we will be focusing more on search, but towards the latter half of the course we will also try to focus on standardized way of representing domains, and we will see logic based approaches for doing that. So, we will do a little bit about logic, representation and reasoning as we go along essentially. Now, search can be of course in many different spaces. We begin with what we call as state space search. So, that is a topic today, state space search essentially. So, let me show you this puzzle which I might have spoken about some time ago. So, you know this is the Rubik's cube, and it has got these 6 faces, and you can move this face, or you can move this face, or you can move any of those 6 faces by multiples of 90 degrees, and so that is a problem that you have to solve. What is the problem you have to solve? That unlike these faces that you can see here, which have mixed up colors, you want all the faces to have only one color. So, every face should look something like this. So, this face is green color, and if I can somehow make the rest of the faces of one color, then I can say I have solved the problem. So, the situation is that I am given this Rubik's cube as it is, and the goal is to solve it, meaning get all faces to have the same color essentially. Now, I am sure you must be familiar with this puzzle. It was devised in the mid 70s, late 70s by an architect called Rubik, and it became quite a craze in those days. People would spend hours and days together trying to solve it essentially. Now, I want to first thing I want to do with this is to highlight the case that between these two approaches to problem solving, search based and knowledge based essentially. If I were to give someone this Rubik's cube who has not seen it before and ask that person to solve the Rubik's cube, she or he would essentially do trial and error. You would try to see what to do with this and what to do with this, and try to explore a sequence of moves which will solve the puzzle. Now, this puzzle is interesting. It looks simple, because as you can see, if you look at the top face, it has got 3 faces. The top face is solved. I have everything green here, and these sides cubelets are of one color essentially. I need to solve the rest. The trouble is, once I have solved this top face, I can only move this bottom face, and there is nothing, no other movement I can make essentially. Remember, there are 6 faces. I could have moved any of those 6 faces. If I am not going to disturb this, I can move only this. but if I move anything else, for example, if I make this change, then you can see that I am disturbing this face essentially, and in the process if I am trying to solve the rest of the cube, I end up disturbing this cube. So, that is why this problem is an interesting problem and has been given quite a bit of a study this thing. Now, how many of you know how to solve the Rubik's cube? Only one, 2, 3. So some people at least. So, notice that the question was how many of you know how to solve the Rubik's cube, which means that if I were to give you this cube, you would virtually without thinking do a sequence of moves which will end up making this solved. So, you are exploiting this technique which we call as knowledge based technique essentially. So, it could be that this knowledge has been given to you in a form of a set of macro moves that to achieve this into this corner, this is a sequence of moves and that kind of a thing essentially. So, that is a knowledge based approach. It is very, once you have the knowledge, it is the very simple way of solving a problem, but the trouble is knowledge has to come from somewhere. And what happens when you have a new problem to solve? Then there is no knowledge to fall back on. It is then that we need to take recourse to search based methods. So, we call search based methods as first principles methods, that you do not have any carryover from the past. You are given a problem and you have to model the problem and you have to find a way of solving the problem essentially. So, it does not matter what the problem is, you can take any problem and we will try to solve the problem. So, one of the things that we want to do in AI is not to solve the Rubik's cube by itself, but to find a problem solving strategy or mechanism which will solve virtually any problem which can be posed as a state space search problem. So, what do I mean by state space search? That I am given the cube, this particular configuration of this Rubik's cube is a state, the desired configuration of the cube is another state, and in between there are thousands of other states essentially, and I need to find a mechanism. So, this state space is a set of states. So, let us say we draw it as a set like this, and I will use S for a start state or a given state and G for a goal state. So, each of them is a state essentially, and there are other states as well somewhere, which we know. Now, how are these? How do we transform the start state to the goal state? We have to have a sequence of moves essentially. So, what are the sequence of moves in the Rubik's cube? So, if I call this as a top face, I can say rotate the top by 90 degrees or rotate the top by 180 degrees or by 270 degrees. So, these 3 moves are possible on this face. More than that, you will come back to the same state. Likewise, 3 moves for every face essentially. So, 6 into 3, 18 moves I have, which I can transform this state into a different state essentially. So, we will model this process as moves which will transform you, take you from one state to another state. Okay. So, in this case I have drawn 6 states. So, if some problem has some 6 moves you can move in a moves you can make in a given state, then the graph would look like that. Now, you can see that this once you incorporate this notion of a move, what is a move? A move is something, an action which takes you from one state to a neighboring state essentially. And given any state, there is a set of neighboring states that you can move to, that is defined by the domain essentially. So, we will assume that we have a function called move gen function, which will take a state as an input and return set of neighbors. So, what we are trying to do is to separate the domain from the problem solving strategy. So, what I am telling you at this moment is that choose a domain and take this as a small exercise that you should try out yourself. Choose some domain of interest that you have, define how to represent a state, and define the move gen function. The move gen function is a function in the programming sense that it takes as input a state and returns the set of neighbors for that state essentially. So, that is one thing that we want. So, let us take another small puzzle. So, if you look at AI textbooks, you will find that they are sort of sprinkled with puzzles, because puzzles are easy to describe, easy to represent, are well defined, and you can do work with them. So, there is this, you might say, a younger cousin of this Rubik's cube, which is on a flat 2-dimensional puzzle, which is called things like 8 puzzle. So, you have 8, 15, 24, in fact any n square minus 1 puzzle. So, 8 is 3 square minus 1, 15 is 4 square minus 1, and so on. So, the 8 puzzle in particular is a puzzle, and you must have seen this, which has got 8 tiles, that is why it is called 8 puzzle. And these tiles have labels on them. So, let us say numbers 1, 2, 3, 4, 5, 6, 7, 8, and this is, let us say, the start state, and the goal state could be something like 1, 2, 3, 4, 5, 6, 7, 8. So, I am not drawing the tiles there, goal state. Now, in this puzzle, I can have, as you can see, basically 4 different kinds of moves, and some people tend to think of it as a movement of this blank. Remember this, so what is the puzzle? You can slide. So, there is a blank square here, blank location here, you can slide this tile here, or you can slide this tile here, or you can slide this tile here essentially, and then in the process you will create a new blank essentially. So, for example, you could do something like this, 1, 2, 3, 4, 6. I could do this. So, this could be a move that I could make, and you can give a label to this move. So, you can either say that you have moved 4 to the left, or you can say that you have moved the blank to the right. They are just equivalent ways of saying the same thing. So, let us say that we call this right, which means I have moved the blank to the right, and then you can see that I can have a up move and I can also have a down move. So, I can generate 3 successor states for this particular state essentially. The whole question is, how do you represent this? So, I will not go too much into that detail, and I will ask you to choose a interesting problem, describe the state representation, and construct the move gen function. So, in this case, the move gen function will return this state and this state. So, it will return a set of states. We will not give too much of importance to the names of the moves at this moment, but later when we talk of planning, we will be more interested in that. So, we are interested in the set of states. Let me take one more example, which is a well known river crossing puzzle. So, you must have heard about these river crossing puzzles, which basically says that in most puzzles there is a boat in which only 2 things can go at one time, and there is a whole set of entities on one side of the river, and they have to be transported to the other side of the river, and there are some constraints about what can go together and what cannot go together. So, you must have heard about the missionaries and the cannibal puzzle. There are 3 missionaries and 3 cannibals, and they have to cross the river, and the boat can take only 2 people. How do they cross essentially? So, a simpler version of that is the man, goat, lion problem. Okay, so, what is this saying? This is saying that I have some river, and on one side of the river there is a man. Okay, I forgot one more thing, there is a cabbage. So, there is a man, there is a goat, there is a lion and there is a cabbage, and there is this boat of size 2, and only the man can row the boat, and the man needs to take everything on the other side of the river, but he can take only one thing at a time. And the difficulty is that if he leaves the goat alone with the cabbage, the goat will eat the cabbage, and if he leaves the lion alone with the goat, the lion will eat the goat essentially. So, he does not want that situation. How can he get his 3 possessions across on the other side essentially? You must have seen this recent movie which this boy and a lion in a boat together stuck for across the ocean. So, obviously, this is a very simple puzzle, it is not hard to solve. The question is not that we are addressing here. The question is that how can we pose this problem or the Rubik's cube as something that we can apply some general purpose methods to solve essentially. So, our goal would be to do something called, our search should be domain independent. The algorithms that we are going to look at should not depend upon the domain that we are trying to solve the problem in. So, it could be the Rubik's cube, or it could be one of these puzzles, or it could be a scheduling problem, or it could be something different essentially. If we can abstract away from the domain, then we do not really need to look at the domain. And what do I mean by abstracting away from the domain? In our case, the first thing is to design a move gen function for the domain, which says that given a state, this function should tell me what the neighboring states are, or should return the set of neighboring states to me essentially. And obviously, when I say given a state, I mean there is some representation of the state that you have to be concerned with essentially. So, how can we represent? So, this of course can possibly be represented as a 3 by 3 array or something like that, and it might be useful to think about it like that, but I will leave it for you to decide. Let us talk about this problem. How do we represent this man, goat, lion, cabbage problem? So, the solution is simple, I am sure you know it. He should first take the goat, then come back with the boat, take the lion, bring the goat back, take the cabbage, come back and take the goat. So, likewise the missionaries and cabbage, all of these puzzles have solutions which are not so hard to find. Can we write a program to do that is a question, without having to write a program specifically for this puzzle essentially. Can we write general purpose programs which will solve puzzles like this essentially? So, there are many other puzzles. The water jug problem, you are given a jug, 5-liter jug and a 4-liter jug, or you are given a 4-liter jug and a 9-liter jug. Can you measure out 6 liters? These kind of problems essentially. So, how do you represent this? So, I want some input from the class, some suggestions. How can I represent this problem? How can I, what is the state representation, and secondly, what is going to be the move gen function? So, the move gen function will be obviously something which will operate upon the representation that we choose. A 3 cross 2 array. Why 3? Why not 4? Oh, okay. So, you are saying that I have a array like this, and this stands for left shore, this stands for the boat, and this stands for the right shore. Is that what you are saying? So, it is an array of what? Because there is more than one thing which is possible on each location. let us just say array of lists. So, it is an array of lists essentially. But how do you write a move gen function? So, what is the initial state? The initial state is everything is in this square. Why do you have two? Why do you have second row? Oh, then you should have 4, I think, right? Okay. So, that is one possibility, I think. But when you create a representation, you should also worry about the algorithm that you will write on the representation, because very often the representation that you choose is helpful in sort of writing algorithms for. In our case, we are interested in this move gen function algorithms. So, let me make another suggestion, which is that I have a list of 2 lists. So, a list of 2 lists, the first list contains things which are on the left bank and the second list contains things which are on the right bank essentially. So, I could choose that essentially. If I choose that list, then my list would look like this: G, this is my given start state and my goal state is but the question is how do I write the move gen function. So, that is the thing that I am trying to derive at what representation is good and what is not good. Now, how would you write a move gen function for this representation? You would have to first search the state. So, this is a state representation. You will have to first. So, we have made an implicit assumption here that the boat, we have not talked about where the boat is, and we can afford to do that because we will make an implicit assumption that wherever the man is, the boat is there essentially, because the boat cannot go by itself somewhere. So, having made that assumption, which is hidden into somewhere here, how do I write a move gen function? I will first need to inspect this representation or this list of lists, find out where M is, and then copy something from there or cut something from there rather along with M and take it to the other side. Something could mean nothing also essentially. So, which means I can go from this state to this could be one successor state essentially. The question is how do I write this successor state. So, I will not spend too much time here, but maybe we will look at one more possible representation. Now, one thing that you would observe is that this second list is redundant. We do not really need the second list. If you know that there are these only 4 characters around, the first list is enough to tell us what the state is. So, that is one thing essentially. And what would the first list represent? It would represent the entities which are on the left bank or something like this. So, let me suggest another thing, which is that you do not represent things which are on the left bank, but you represent things which are on the side of the boat and you also represent which side the boat is essentially. So, which means instead of this I would have something like this. So, let us say I do not represent the man, I am just trying to explore different possibilities. I just say left GLC and this is my representation. So, what I mean by this is the boat is on the left hand side and which means the man is also on the left hand side, and along with the man there is the goat and the lion and the cabbage alongside. So, the advantage I see of this representation is that my move gen function would be simpler, at least that is what I feel, because it is going to be symmetric, whether I am going from left hand side to right hand side or right hand side to left hand side, the operations that I will have to do would have to be identical, which means that I will delete some elements from my list and create a complement set, which will be the new list essentially. So, for example, from this I will delete G and take it to the right hand side. So, this could be a move essentially, or if I want to represent the same move, I will delete L essentially. So, I have taken the lion to the other side essentially. Not a very good move of course, because the goat will eat the cabbage, but the state space algorithm has to search through all possibilities. So, we are trying to look at that essentially. So, I would leave it as an exercise for you to try out different representations for this and see and actually write a program which will take a state as an input and return the set of neighboring states as the output. So, there are 3 moves possible in this case. In fact, there are 4 moves possible. The man can go alone, or the man can take the lion, or the man can take the goat, or the man can take the cabbage. So, it should return these 4 sets as my output to the function, and this move gen function is a function which will allow me to navigate the state space. So, I will apply the move gen function to this state, I will get a set of neighboring states, I will go to the neighboring state and see if that is the state I was interested in, otherwise I will apply the move gen function to that state, and in this process I will navigate the state space trying to reach the goal state that I am interested in essentially. So, this general strategy that we are going to follow has a generic name which is called generate and test. It says generate a candidate and when you say candidate, we mean a candidate state, and test whether it is a solution. And we put this into a loop, and this is a high level strategy that we are going to refine over the next few weeks. I think generate a candidate and see if that is the goal state that we are interested in. Our task is to explore this state space in search of the goal state essentially. So, we will keep trying out new states and seeing whether that is a goal state or not. How do we see whether there is we are in the goal state or not? We need another domain function, and that domain function we will call as the goal test function. So, goal test will take a state as an input and output either yes or no. It will tell me whether the state that I am looking at is a goal state or not a goal state. These are the only 2 functions I need which need to know anything about the domain at all. So, once I have written these 2 functions for a domain, I can practically forget about the domain. I do not have to worry about whether I am solving the Rubik's cube, or whether I am solving this 8 puzzle, or whether I am solving this river crossing puzzle. It does not matter. I have a move gen function, I have a goal test function, and I want to find a sequence of moves which will take me to the goal test, and so this is a very abstract problem essentially. Incidentally, while we are at the Rubik's cube, only very recently, and by recently I mean in the last 5 to 10 years, have search algorithms been able to search for optimal solutions of a problem like this essentially. And by optimal solution, I mean the shortest, smallest number of moves that you need to make essentially. If you follow the method that somebody has taught you, which says take the top layer first, then make the second layer, then get this bottom corners or get the bottom square, and then get the orientation. So, these kind of macro moves, they will not necessarily give you the shortest solution essentially. So, they will solve the problem, but they will not give you the optimal solution. So, this is something that we had also mentioned about human problem solving, that we do not necessarily always try to optimize things. As long as we can solve the problem reasonably well, then we are happy with the solution essentially, which is why knowledge based techniques are so important essentially. Okay. So, the move gen function for this would be an interesting exercise. As you can see, there would be 18 possible moves for every given state, corresponding to the 3 moves for each face. So, there are 6 faces. So, any of those 3 could give you a move gen functions. So, you can see that the state space for this is quite large essentially, and that I can leave it as a small exercise for you to see how many possible different configurations there are to this puzzle. Okay. So, what have we done? We have abstracted away from the domain, and we are only going to work with these 2 functions. So, the algorithm that we will write now, you will just use these functions and do not worry about what the domain is essentially. And what is the idea that once we have designed these algorithms, then we can plug in any domain and it will solve problems in the domain for us. So, there is this generality about our approach essentially. So, let us define this algorithm a little bit and we will call it simple search 1. So, let us work with sets for this moment. We have to see when we generate these successors or neighbors, we have to store them somewhere, and we will store them in a set which is traditionally has been called as the open list or open set essentially. So, we begin by saying open gets the start state. So, we put the start state in the open and do the following: while or instead of y, let us say true, remove I am using the set union operation. Okay, so, I forgot one step, and the step that is going to be here is pick some node n from open. So, let us call this n now. Because we are not only talking about the start state, but of any node that we pick from this list, this set open. So, what is this refinement of this algorithm is I create this open set called open, in which I put the start state to begin with, and in general my algorithm says pick some node. So, we are calling it a node because we are sort of already started thinking about this as a graph over which we are searching. So, each state is a node, pick some node n from open, test whether it is a goal state. So, the generate and test idea. If it is true, then we should return we have found the solution. If it is not true, we will remove this n from open and add instead the successors of open or the neighbors of open to this. So, I will keep adding things to my open list and keep picking some element from that, testing for that. So, that is the simple basic idea we start off with essentially. What this results in is a search tree. We will start by criticizing this algorithm very shortly, because this is by no means an interesting algorithm, but it gives us a basic idea of what we are trying to do. What this algorithm does is it generates a search tree. Okay. So, one thing that I should sort of clarify is that even though we see the state space as a graph, because from every move you can go, every state you can go to neighboring states. So, every edge is a move from one state to a neighboring state, and the whole state is a graph. And essentially what we are trying to do is to find a path from a start state to a goal state in this graph essentially. So, it is basically the graph search algorithm that you must have encountered in some other this thing. The only difference here is that the graph is not given to you, that nobody says that this is the entire graph for the Rubik's cube for example, and then find a path essentially. You have to generate the graph on the fly, and that is done, that is what generates the search tree essentially. Okay. So, we can visualize what is happening with this algorithm. Now, notice that there is a very, I do not know whether you can read this, pick some node n from open. So, this sum node is there, and a considerable amount of time would be spent on refining this notion of sum, because it really critically depends upon this sum as to whether you are heading towards a goal or not heading towards a goal essentially. So, we will spend some time on that, but as of now we will have say that okay, we have not specified it. So, use some criteria to pick a node from open. And so, what is the search tree we are generating? We start with some search, the start node S. So, we will use state versus node interchangeably, at least for now. So, search node is equal to state, the same representation. We will move away from this in a moment. So, the first, the root node is the search start state or start node, and we inspect that root node. What do we mean by inspect? We apply the goal test function and we see whether that is a goal, because sometimes the problem may not need anything to be done essentially. You know, it's somebody gives you a solved cube and says solve it, you will say here it is solved already essentially, you do not have to do anything, but so you must test whether it is a this thing. So, we inspect the start state or the root node, and let us say that this double circle stands for deleting it from open. So, what I am drawing here is open list. I had S in open and then I delete it, but I replace it with some successors of S. So, my open has now got four successors. So, for example, in this situation I would have added 3 successors because of the 3 moves I can make, or in this situation I would have added 4 successors. So, depending on the state, some number of neighbors would be generated and they would be added. Then my algorithm says pick some node from open. We have not specified which node. So, let us say we pick some node and we generate, add its successors to open. So, this is a general process that our search algorithm is going to follow. We have this set of open nodes, we will pick one from there and see whether that is a goal node or not. So, this actually reminds me of this in a moment. Green, this interesting story about Hercules and Hydra in Greek mythology. So, I do not know how many of you have heard about this story. So, Hercules is fighting this many headed monster called Hydra, and the problem is every time he cuts one head of the Hydra, many more appear essentially. So, you can see that is what our search algorithm is facing. Every time you cut one head or one node from the search tree, you get many more. So, as you can imagine, the open set is growing and growing, and we have to find a way of solving this. So, it does not have to be this, the next one could be, so this is let us say number 2, this is number 3, this could be number 4. We have not specified which node to pick, we will do that in a moment.
So, how do you know that you will end up with a tree? What stops you from going in a cycle?
Yeah. So we will start criticizing our algorithm in a moment. So, his question is what stops you from going in a cycle. So, that is in fact the first problem with our search algorithm. I was about to ask you what is wrong with this algorithm, and that is the first thing which is wrong. And so, if I take this for example, Rubik's cube again, I can say make this move, rotate right, this right face by 90 degrees. Then what are the moves available to you? Out of the 18 moves that are available to me, one of them is this one. Say, what if I choose this? Then what if I choose this? Then what if I choose this? Then I have got caught in a cycle essentially. And of course, you can imagine that there are hundreds of cycles hidden there. I can just keep rotating this, that is another cycle, or many other things are possible essentially. That is one problem with this. So, let us first address that problem. So, one way of thinking about these search algorithms is to imagine that you are in a maze. Okay. So, they used to have these mazes in olden times, where there is some. So, you are at some corner and you can see 4 roads. So, you are inside some building, you can see some 4 paths going, you go to this path, then you see another 4 paths and so on. So, this is like a node and this is like an edge. So, you move from here to here, you see more nodes. How do you get out of a maze without getting lost, without getting into cycles? So, there is again this another interesting story from Greek times. I do not remember who was this person who solved it by taking a thread along with him and said that he will mark every path with the thread. So, if he sees the thread again, then he has he knows that he is back to that something, some state that he has visited before. So, in terms of looping, what do we want? We want our search algorithm. So, if I am going to start with this particular state, I do not want to come back to this state by going through a sequence of moves. I have to somehow prevent that, which means once I have made this move from here, I should never visit this state again. How do I do that?
Mark that state as visited and we won't come to that state.
Mark that state as visited. That is the simplest way of doing it. And traditionally, what we do is we introduce another list, and well, I have already started calling it a list, because pretty soon I will be calling it a list. Another set, let us say, and we call it closed essentially. So, the algorithm is modified as this. So, this is simple search 2, open as before gets the start state, closed as is a new this thing which starts with the empty set, and pick some node from open. So, the same and the new step which is add it to closed. I can write it as a set notation, but anyway I am writing it in English. Then, so let us say that node is n as before, if n I do not know whether you can read this, I should write a little bit more carefully. If goal test n, then return n, that is what I am saying, just return the state, else as before add. So, what should I add to my open now? Union what? Move gen n minus anything in closed, and let me improve upon that a little bit and say even anything in open essentially, because it is possible that 2 states may be generated by the same successor may be generated by 2 states essentially, 2 different states essentially. So, for example, I can start with this state, then go to this state, then go to this state, and this state would have generated this state would have generated a 180-degree move where I could have gone here. So, it would have put it in open or not that move, let us say this one. Okay, so, let me start again. At this point on my open list is a 270-degree move, which will bring the green thing here. So, I have added that to open, but I have made this move. From this move I can make a 180-degree move, which will again bring the green thing here, but I do not want to do that because I have already added this in the open list essentially. So, you just think a little bit about that. From this I will remove the set open union closed. So, I will not add any node that I have generated before or seen before to open. My open will only get new nodes essentially. So, this will stop me from going into loops essentially. So, there is this if, right. What if move gen this thing does not add anything new, then I am also getting into a loop of some kind essentially. So, I should have a test here, pick some node from open. If open has become empty, then I should say there is no possible solution. So, I am not adding it right now, but we will add it this thing. How can open become empty? If you have seen all possible states and the solution state is not available to you. So, for example, this puzzle, that 8 puzzle that you know, all the permutations of these 8 tiles are actually into 2 disjoint spaces. So, there is one graph where you can navigate from one set of states to any other state, but there is a disjoint set where you can also move from one set to another set, but you cannot go from this set to that set essentially, and that can be obtained with simply by flipping two tiles essentially. They are in disjoint states, you can never get them back. Likewise, the Rubik's cube. So, this is a trick which some people know. You can take out this thing and reassemble the whole cube essentially, but the thing is you can reassemble the cube back in 12 different ways. So, it is possible that this particular set of states contains my goal state, but another set of states does not contain the goal state. There is one more problem with this algorithm or this algorithm, which we will. So, I will stop here now. When we come back, we will look at what this other problem is. So, I want you to think about this in the meanwhile, and when we come back, we want to look at this, what is the second problem with this state, and try to address that. And after that, we will look at the behavior of different strategies. When you say sum, what are the options available to us, and how do they change the behavior of our search essentially. So, we will do that in some sense in the next class, which is after 5 minutes.